In this video, I'd like to show how to graph a logarithm in one of these two forms. It turns out that any transformed logarithm function can be written in either of these two forms, the first of which would be if you did not horizontally reflect, the latter of which would be if you chose to horizontally reflect. In either case, x equals b would be your vertical asymptote. Notice in this video I chose to use a base 10 logarithm. It turns out any other base would be algebraically equivalent to a vertical stretch or compression, which I've taken care of by using the letter a here as a coefficient on the logarithm. Also note that I chose to put a coefficient of 1 on the x. Any number other than 1 would be normally considered as a horizontal stretch or compression, but this can be shown to be algebraically equivalent to a vertical shift, up or down, which I've compensated for by adding k at the end of each of these equations. Here is a graph of the logarithm base 10 function where a is 1, b is 0, and k is 0. Notice if you were to replace a with 1 and b with 0 and k with 0 in the general formula, you would get this function which I've colored blue, 1 log base 10 of x. Notice when I vary a, b, and k in the video, there are three things that remain true. The vertical asymptote of the function will always be x equals b. Right now b is 0. The range of the logarithm will always be all real numbers, regardless of these three values. And logarithms never have horizontal asymptotes, regardless of these three values. I'm going to vary these parameters one at a time. Notice when I move the slider for a, left and right, if a is bigger than 1, that has the effect of vertically stretching the logarithmic graph. When a is between 0 and 1, this will have the effect of imposing a vertical compression on the logarithm. But notice as I'll move the slider left and right, focus your attention on the point 1, 0, and notice it will not change. The horizontal intercept will be constant, regardless of the a value, and the vertical asymptote will remain x equals 0 because I'm leaving b to be 0. So once again, notice that the horizontal intercept does not change and the vertical asymptote x equals 0 does not change. Changing the value of a has the effect of either compressing or stretching relative to the original logarithmic function. Now that I've reset a to be 1, let's see what happens as I change b. Let me slide over so that b is 1. Notice that I've chosen b to be greater than 0. In fact, I chose it to be 1. If you were to place b equals 1 in the general formula, it would be the equivalent of having an x minus 1 in the parentheses, which moves the graph to the right 1 unit. If I was to replace b with negative 1, then notice because we're subtracting b, you'd have subtracting a negative 1, which makes a plus 1 in the parentheses, which moved the graph to the left 1. Notice that this changed the horizontal intercept. So as I change b to the right and to the left, you can see the graph sliding left and right, which changes the domain of the logarithm, the horizontal intercept, and the vertical asymptote. Now that I've reset a to be 1 and b to be 0, let's focus on what the value of k does. If k is positive, you'll be adding a number to the function values, and the graph should move up. If k is less than 0, you'll be adding a negative, which is the equivalent of subtracting a constant at the end of the function, and the effect should be that the graph would move down. So as I move to the right, you're adding larger and larger values to the function values, which moves the graph up. Moving the slider to the left gives me negative k values, and if k was less than 0, you'd be adding a negative number, which is the equivalent of subtracting a constant at the end of the function. And notice as I subtract larger and larger values, at the end the graph goes further down. So k moves the graph up and down, which would change your horizontal intercept, but does not change the vertical asymptote. In fact, the vertical asymptote will be 0 because I've let b be 0. Lastly, this part of the video will remind you that one last kind of transformation that you can impose on a logarithm is a horizontal reflection. Notice that with a non-transformed logarithm, the graph of the logarithm usually goes to the right forever, but now having put a negative here in the equation in this position, the graph goes to the left forever rather than to the right forever because it has been horizontally reflected. But I want to show that the values of a, b, and k take on the same exact meaning. For example, if a is bigger than 1, watch the graph vertically stretching. I've reset a to be 1. I'm going to move to the left. And if a is between 0 and 1, this will impose a vertical compression. So let me just change the value of a, and notice the horizontal intercept is now negative 1, 0, and the vertical asymptote is x equals 0. Now that I've reset the value of a to be 1, just like with the logarithm that was not horizontally reflected, having b being greater than 0 will move the graph to the right. Notice I changed b to be a negative 1, By substituting b equals -1 in here, you'd be subtracting a -1 or having a +1 in the parentheses, which would have the effect of moving the graph to the left. In fact, this happens for any b values less than 0. So let me just move the slider b back and forth, and you can see that the vertical asymptote changes, and so does the horizontal intercept. But notice, as I said before, logarithms never have horizontal asymptotes, and the range is all real numbers regardless of these three values. Finally, remind yourself that k, if positive, will shift the graph to up, and if k is negative, less than 0, the graph would move down. So as I move k to various positions on the slider, it'll take on positive and negative values, moving the graph up and down, and notice that the vertical asymptote does not change, the range does not change, but the graph has just simply moved up and down.